Hello again. So now let's study about the general characteristic of materials. So let's start with the general characteristic of metals. So metals are widely used in our everyday application. It can be used for construction. It can be used for the tanks or for the chemical plants. It can be used for pipelines and so on. So in this picture, this one, the first picture here is the metal sheet, which is coming out from the metal processing facility. This picture shows liquid metal that is cast. So this is the casting, how to cast the metal into some form, for example the machine's block. And this one, the metals where there's a block of metals and it is machined to make some holes or some requirements. And the last one over here is about the metal also can be used make into fiber and do metal fiber or cables. Okay, so what is the general characteristic of metals? The first one is metals is generally stiff, and then it has high elastic moduli, and then when it's pure, it is very soft and also easily deformed. You can bend it with your hands, let's say, but when you put some alloying or make mechanical treatment or heat treatment, it can be strengthened. So basically we can change the properties of metals by adding alloying or mechanical and heat treatment. It also ductile, so you can form it, you can bend, you can make it into shape without any crack. And also it's tough, which is it can absorb energy. So if you have an automobile and then if you have if you have a car and then the car is crushed, usually the top part or the front part of the car will crash, and then it won't broken, but it's just gonna crash and absorb the energy. However, the metals is least resistant to corrosion. And then the second group or the second family is called ceramics. We found ceramics in everyday activities as well, in your mug, in your maybe concrete, for example. So this picture shows you what's inside the furnace. The line of the furnace is made from refractory bricks and it's made from ceramics. This picture shows you about how to make a concrete of a building. We can see these lines actually from the steel, the carbon steel for the to strengthen, but then the worker here are put some mixture of cement and also sand and so on to make the concrete. So and then you can also see ceramics in a part of our laboratory. So this is the glass use the reaction tube for the laboratory. And then this is a type of ceramic in the pipeline. So the ceramic will line these pipelines to make those pipeline can support maybe some corrosion prone materials without having too much cost for the pipelines. So the ceramics is actually very high moduli, very stiff compared to metals. It's higher than metal, of course, for the high moduli, and it's brittle. It's not ductile. Metal is ductile, you can bend it, but for a ceramic you cannot bend it without having it crack. And the compression strength is usually much higher compared to the tensile strength, so it's able to withstand some compression compared to able to withstand the tensile there. And then it is very stiff, very hard, and also abrasion resistant, and also use corrosion resistant, so it can be used for lining the pipelines. It retains strength as well in high temperature, and it varies between glass, non-ceramics to crystalline or amorph ceramics. And then how about polymer? Polymer, we see everything lot in pipelines, in your plastic bottles, in your in almost in every day activities. It has low moduli, which is it is very easy to do the elastically or plastically deform. It can attain high strength. For example, it will exhibit large elastic deformation. It can be cast like this to put the die in casting. It's prone to creep, which is prone to deform even at room temperature. And it has thermoviscoelasticity behavior, so it would be more elastic at higher temperature. It doesn't exhibit useful strength at above 200 degrees Celsius. It's easy to shape, easy to cast, and very, very corrosion resistant, and also low coefficient of friction. Okay, so this is actually shows some example of significance of material selection in cost. So this is the type of CNG tank, the compressed natural gas tanks, and then this is the tank. So if we look at over here, there is the cost breakdown for modeled IV CNG pressure vessel at multiple production volume. So this is the cost, and then this and to make the vessel, if you look at it, there are a number of components to make the vessel, and this blue over here is the line formation or the material formation, as well as the boss or the material and procurement. Here that the higher vessel that produce, here the material cost is significantly reduced, so and then it hence will reduce the total vessel cost. So that's why the higher vessel you can make, it cheer the lower material cost for per unit, and also it will lower the vessel cost as well. Okay, this is the example of material selection significance, the process plant integrity. This is a case of Humber estuary from the UK refinery explosion in April 2001. It caused by catastrophic failure of a gas pipe that under thinning over here on the bending due to the aeration and corrosion. And then there's a catastrophic failure, and the damage total up to $82 million. And then also the company also required to pay fines and repair costs to the coal community over £1 million. Okay, another one also how if we want to make a tank for different purposes, from the palm oil tank, and this is from the milk tank, or this is for the CNG tank. So both of them have different safety, health, environment consideration. For example, for the CNG tank, you will need more thickness because it is pressurized, and you need stainless steel for the CNG for the milk tank, of course, because it should be can be used for food processing, and this one is for, it can be just carbon steel or dunocosmic steel to make for the oil tank. Okay, this one also the famous material failure, Titanic. So in the Titanic, some of the type of the failure is actually caused by the iron rivets. So this is the body of the ship, and then it is fastened and tightened by the called rivet, and the rivet is from the iron rivet, and then the rivets were used to seal the hull plates together with the hammer at the end of the exterior, and the pressure from the iceberg collision may cause the rivet to pop along some hole cause seam to open, and the totally open seam may no bigger than a closed door through then the 34,000 ton of water seep can go inside the ship. So I think the contact of within the iceberg was probably a series of impacts that caused the river to fail in the shear or the elongation. Another famous material failures is the airplane, the Havilland Comet airplane. So it was a first commercial jet airliner designed to fly higher and faster. And in 1949, there are a sudden failure, which is this airline are breaking up in the air, and then it is caused actually by the metal fatigue due to the prolonged cyclic different pressure on the ground of the atmosphere, and also from when they're flying. So after a while, the metal fatigue without anything happens, then that would be a broken of those airplane. Okay, then another one would be the famous material failure with the space shuttle Challenger here, because it's actually based on those O-rings. So this O-ring is a very small part of the like made from the rubbers, and then here, because of this, there is a leaking because it was cold, so the O-ring become very brittle, and then there's a leak and then crack around here of the O-ring, so the nitrogen liquid tank were leaking, and then contact with the fire from here, and then after that would be of course it would be a failure, and all the crew aboard were killed. So those material failures will give some lesson to us engineers how to design material should be economical, of course safe, and then applicable to the application we want. Okay, I hope you enjoy this lecture. You can learn new things from this lecture, and I'll see you again soon. Bye bye.